In this video, we're going to talk about acetal formation from aldehydes and ketones. Let's start off with looking at what an acetal is. So an acetal is when you have a carbon with two ester groups attached. So it kind of looks like a diol with two alcohols, but instead of two OH groups, it's two OR groups. So we're going to start off with our aldehyde or ketone. We will add an alcohol. And we're going to need some acid present for this to work. And what we end up with are two of the same OR groups attached. So this is again an equilibrium reaction. It is again carbonyl favored, so it's not a product favored reaction, it's actually a reactant favored. We can push this reaction towards products by removing water. So a byproduct here is water. And so if you can set up your reaction to remove that water, you can push the reaction towards products. One thing that is nice about this reaction and when it's most commonly used is this acetal can act as a protecting group for ketones and aldehydes. So if I have a ketone or aldehyde in my starting structure and I want to do, say, some kind of reduction to an ester that's also in the structure, the acetal will selectively add to the ketone or aldehyde and then protect it. Then I can go through reduction steps that will only affect the ester. And then I can go back and remove the acetal and reform my aldehyde or ketone, which would have been reduced had I not protected it. One very common alcohol that's used, it's actually a diol. And this is used because whenever we form the acetal, what you actually get is a linked, so instead of two kind of separate OR groups, it's one that's linked together. One reason for doing this is, well, you'll see here in the mechanism in a minute, this is a little bit faster because the second alcohol that it needs to react with is right there because it's already attached to the starting material. This reaction is reversible with acid. That's how we would remove a protecting group. So let's look at a specific example. So I have a molecule that has kind of what I suggested earlier, a ketone and an ester. And I want to do this reaction. So I want to keep the ketone, but I want to reduce the ester down to an alcohol. So if I were to just add a reducing agent here that would reduce the ester down to the alcohol, it would also reduce the ketone down to an alcohol. So I need to do something to protect that ketone first. So I'm going to do this acetal formation. And you don't have to use this particular alcohol, this diol, but like I said, it is commonly used when you're doing just the protection. So that's going to selectively react with the ketone, and we get the acetal formation at that spot. The ester remains the ester. Now I can add my reducing agents, and lithium aluminum hydride will do the reduction. So that reduces the ester down to the alcohol. The acetal remains untouched at this point. And it doesn't reduce. However, because I added acid in the second step, that acetal really actually is removed at the same time. A lot of times it is shown as a separate step just to kind of reiterate in your brain, but it is going to all happen at once because once you add acid, that protecting group is gone. It won't selectively just do the second step of the reduction, but that's fine at that stage. So here is an example of how we use the acetal as a protecting group. If we want to look at the mechanism for this reaction, again, nucleophilic addition reaction. If we start with our carbonyl, because we're in acidic conditions, and it's acidic from the beginning, we're going to first protonate the carbonyl oxygen. Again, this makes for a better electrophile, which is necessary because our alcohol, which is our nucleophile, is not a very good nucleophile. But now that we have the activated carbonyl, it will attack. We will form our tetrahedral intermediates. At this stage, again, we're in acid, so water is going to come in and deprotonates. Still in acid, so that acid is going to protonate the alcohol group. Now I have a good leaving group, so what's going to happen is a lone pair from the ether is going to kick down and kick off the water. So this should look very familiar to what we had with our protonated starting material. Again, we have an activated carbonyl, so another molecule of the starting alcohol will come in and attack again. And we basically repeat this process. We have a tetrahedral intermediate again. We will deprotonate with water. And now we have our acetal product. So this mechanism, you're, again, like I said, basically repeating the same thing twice. First adding the first alcohol group, making water leave, adding the second alcohol group, and ending up with your final acetal.